Hello everyone, my name is Likit Sai Krishnamsi. I am from AI second year. My roll number is 23027 and today we are going to discuss about the topic key value representation of sparse matrices. So let's get into it.
Hello everyone. So the topic we are going to discuss today is key value representation of sparse matrices. And before we go deeper into this topic, let us first know what sparse matrices are. So sparse matrices are basically those matrices which have a majority of zero elements compared to non-zero elements. So for example, let us take this matrix, and as we can see, there are majority of zero elements compared to non-zero elements. So this makes it a sparse matrix. Now let us get to know the characteristics of sparse matrices. Storage. Since there are few number of elements in sparse matrices, fewer elements can be stored in a given amount of memory. Computing time. We can traverse and search through the sparse matrices without having to spend more computing time. This makes the sparse matrices an efficient way or representation of a matrix. Sparse matrix representation. A sparse matrix can be represented in a three-column representation or COO format. In the COO format, only the non-zero elements are stored along with their row and column indices. This format is especially efficient for storing sparse matrices where the most elements are zero, as it saves space by only keeping track of the essential elements. Now let us get into the structure of COO format. So three-column representation has row indices, column indices, and values. And these arrays, row indices array stores the corresponding row value of non-zero element, and the column indices stores the column value of the corresponding non-zero element. And the value array is used to represent the non-zero elements themselves. Let us take an example to get to know the COO format or three-column representation mode. Let us take a matrix. So to represent this sparse matrix in a three-column representation, first we have to take a row array and a column array and a value array. And later the row array has to be from zero. That should start from zero. And the column array also has to start from zero. And for the first row, the first non-zero element is on the first row and second column, which is 1. So 0 and 1. And the second element is on the second row and first column, which is 1 and 0. And the third element is on second row and fourth column, which is 1 comma 3. And the fourth element is on third row and third column. Now we have to represent the non-zero elements in this particular matrix: 1, 2, 5, and 9. So this is basically three column representation for this matrix. Now let us know about compressed sparse row, which is also a type of representation of sparse matrices. A compressed sparse row format is a popular way to store sparse matrices, especially when row-wise access is needed. Compressed sparse row compresses the sparse matrix by storing only the non-zero values and uses additional arrays to mark the row, column, indices of these values. Let us get to know the structure of CSR format. So first we have the values uh, where we have to store the non-zero elements in the matrix. Column indices. The column indices store the column index of each non-zero value and the row pointers. I will tell you about the row pointers more when we get into the example. So let us take a matrix. Let us take this matrix. So first we will write the value, column, and the row pointer. For the given matrix, there are a total of four non-zero elements. So let us write them: 3, 2, 7, and 1. And we have to represent which column these particular non-zero elements are. So the column has to start from index 0, 0, 1, 2, and 3. So the first element is on the second column. So 2. And the element number 2 is on first column, 1. The element 7 is on 0 and 1 is on 1. Now we have represented the value and column. Now for the row pointer, a row pointer always has to start from 0 because it means the first row starts at index 0 in the value array. And now we have to see how many elements are there in the first row. In the first row, there are total of one. There is a total of one element. So we have to write one here. And in the second row, there is also one element. So we have to add the element in the first row and the second row. So there are total of 1 plus 1, 2 elements. And in the third row, there are total of 2 elements, but we have to add all the elements from the row 1 and 2 and the 3. So there are total of 4. So this is a simple way of representing the row pointer for a compressed sparse row. And these three gives us the CSR format for the given sparse matrix. Now let us get into the main topic, key value representation of sparse matrices. The key value representation is another way to store sparse matrices, often implemented as a dictionary or hash map. In this representation, only the non-zero elements of the matrix are stored with their positions as key and their value as values. This approach is straightforward and highly flexible. The structure of key value is as follows. The key value representation of sparse matrix contains a key and a value. A key contains basically a row and column representing the position of non-zero element, and a value is a non-zero element itself. So we write it as key and value. The key contains a row and a column of the non-zero elements, and the value is basically the data. Now let us know about advantages and limitations of key value representation. Advantages: flexible access. Since non-zero values are stored with specific row and column keys, it is easy to look up, add, or update individual elements. Space efficiency. Only the non-zero elements are stored, making it memory efficient for highly sparse matrices. Simplicity. This format is intuitive, and easy to construct, especially in languages with dictionary or hash map. Dynamic modification. Inserting or deleting elements is straightforward, as it is simply involves adding or removing key value pairs. Now let us get into the limitations of key value representation. Inefficiency of a large matrices. For very large matrices, dictionaries or hash maps may introduce overhead due to hashing, which can slow down performance. Poor for ordered operations. Row-wise or column-wise operations are less efficient because the elements are not stored contiguously in memory. Higher memory overhead. Compared to array-based formats like CSR or COO, this format may use more memory as each key requires additional storage space. Now let us get to know an example for representing the key and value of sparse matrices. Let us take a matrix of 1, 0, 0, 2, 0, 0, and 0, 0, 3. And for this matrix, there are total of 3 non-zero elements. So we need to write the key and a value for this matrix. So the row 0, 1, and 2, and the column 0, 1, 2. So the first element is on 0th row and 0th column. So 0, comma 0 contains 1. And the second element is on the first row and 0th column. So 1, comma 0 contains element 2. And the third element is on second row and second column. So 2, comma 2 contains element 3. So this type of representation is a key value representation of sparse matrices. And that's all. Now let us get into the code.
So now let us see the code for key value representation of sparse matrices. First, we have to import java.util hashmap and java.util scanner. The hash map is used to represent the keys and value for the sparse matrix. Next, we have to take a class called sparse matrix and define a hash map of type string and integer. Next, we declare a constructor and initialize rows and columns to it. Next, we take a function called set where we use it to set values to the row and column of the matrix given by the user. Next is the display function, which is used to display the sparse matrix after the input values have been given by the user. It returns a empty if there are no elements in the matrix. Next, in our main class, we give a scanner command and we take inputs from the user for the number of rows and columns for the given matrix. Next, we ask the user to give row by row matrix element. So we take the set function here, which takes the user input here and maps it to the given matrix. Next, it helps us display the matrix, and we are closing the scanner here. When we run the code, we first write the number of rows and columns we need. Then we enter. So now we can see we inputted number of rows as 4 and number of columns as 3. And I have given a matrix row by row. There are a total of 4 non-zero elements, and this is a sparse matrix is the number of zeros are greater than non-zero elements. And here for the sparse matrix representation, we can see at element at position 1 comma 0, there is element 4. And at the index 0 comma 2, there is a element 3. And at the index 2 comma 1, there is an element 5. And at index 3 comma 2, there is an element 7. And this is how key value representation of sparse matrix can be done.